off to I'm gonna go with 13. Sounds like a good number. How about that? All right. So this is chapter 13. We're going to get into equilibrium this chapter, and frankly, it is really the setup for most of the calculations we're going to do in a majority of the chapters. Really do involve sort of these equilibrium sort of calculations that we'll do in this chapter. And the next several chapters, as we talked about, we'll kind of be peeking into like the really tough part of the course. And, it does come back to sort of the calculations that we do here. We just kind of change a little bit here or there along the way. So let us talk about equilibrium and chemical equilibrium. So first off, equilibrium and chemical equilibrium really revolve around a specific type of reaction, and those are really reversible reactions. So those reversible reactions, as I think we might have spoke about last time as well, these are typically the guys that have the arrows basically heading in both directions. And what that really means is, as we were talking about with, I think, mechanisms where we came across this, is it does have a forward direction that is heading from reactants to products. But at some point, what will happen in these type of reactions is you will build up enough products that they will decide they also want to sort of start to react with each other. And what that ends up happening is shoving the reaction in the opposite direction, where really the products are recombining to form reactants. And that is what is known as the reverse direction. Now, a very common mistake that people make when they think about equilibrium and something that has reached equilibrium, and the name, I think, is what sort of hurts people sometimes on this, is people think that when a reaction reaches equilibrium, you got pretty much like the same amount on both sides. And that's not necessarily what it means. It's really not what it means. What actually it means when we reach chemical equilibrium is actually what we were talking about in the previous chapter. It means that the rate of the forward reaction will equal the rate of the reverse reaction. And that really is what it means when a reaction reaches chemical equilibrium. And basically what that means is, as fast as it goes from reactants to products, it's just as fast going to come back the other way from products back to reactants. So what that ends up doing is, when it reaches equilibrium, it pretty much locks everybody into place as to where they were in terms of their concentration, in terms of their pressures. So for example, if we started with like 4 molar of A and 4 molar of B and nothing of C, this thing reaches equilibrium. Maybe we end up with like 2 molar of A, 1 molar of B, 3 molar of C, 3 molar of D, for example. And once it reaches equilibrium, basically what that means is those guys will be able to maintain that concentration, because pretty much as soon as it breaks down a little bit, it comes back the other way at the same rate. So that's an important thing to keep in mind as we talk about equilibrium. The other really important thing, which is sometimes a hard concept for people to understand as well, is there's different points along the way in the chemical equilibrium that you can sort of start at. And what I mean by that is, when you start with a certain amount of reactants, maybe you start with a certain amount of products, you can start with different amounts. This reaction will come really to rest at equilibrium with really the same proportion, as we'll talk about, of sort of products to reactants. So let us talk a little bit more about this here. So as I mentioned before, what we're really looking at here is the state where the concentration of the reactants and the products, they will remain constant once that equilibrium is made. And they will basically be able to maintain that constant amount of their concentrations, as long as you don't do anything to kind of screw up the equilibrium, which we'll talk about later in this chapter, what happens when you screw up the equilibrium. But as long as you really don't do anything to it, as long as the temperature remains pretty much the same, everything will stay in that nice equilibrium state as going back and forth. What that also means is, when you look at, for example, a beaker that you did one of these reactions in, and you may look at it and maybe, hey, it started like red in color and then it ended sort of colorless. And when you look at the reaction, you may look at it and go, well, there's not much happening and the reaction is over. And actually, if you were to sort of zoom in on the molecular level, you would see a lot of activity. So if this was like our reaction of A plus B goes to C plus D, even though the beaker may look really unchanged to you for a period of time and stuff, if you really zoomed in, you would see a lot of A and B going this way. Then you'll see some C and D coming back that way. Again, they're just doing it at the equal rate, which to you on sort of the big level may look like it's all done, nothing's happening, but there is a lot of activity that continues to occur in an equilibrium constant, even when you may think, it's over. Hence, microscopically there, it is static. Again, it may look done to you, but microscopically, if you zoomed in, lots of activity happening to maintain that rate of the forward and reverse reaction occurring at the same time. So if we look at this reaction, which I'm going to go with ammonia formation here, looks like it. And since it's chemistry, I probably should balance it like a good chemistry instructor. I'm not sure I am that, but we'll do one of those anyways. There we go. So at the very beginning of time 0 here, we can see on this graph, we have basically have all reactants at this point, and we really have no products. So what's going to happen in this sort of situation is, because we really have all reactants to begin with, we would expect really the forward direction pretty much to occur. That's pretty much all we got to work with. So at the very beginning of this reaction, we would expect this reaction really to proceed from reactants to products. And that's why when we look at the concentration of our reactants, we start to see it decrease here from where it started. And at some point, obviously, when those reactants come together, we make some products here, which means we start to see our product concentration really start to increase. At some point along this journey here, we do get this point where pretty much all of our guys flatline here, right? They all plateau. Just really badly scribble over that there. So they all basically plateau out there. That means, are their concentrations changing at this point? They're not. They're pretty much constant. So that point where we start to see, obviously, the plateau of everybody is basically where chemical equilibrium has been reached, because at that point, like I said earlier, pretty much everybody has just locked themselves into whatever concentrations they may be at that particular point. As you can also see here, none of these are exactly the same concentration in this particular example. So again, equilibrium doesn't necessarily mean equal. It just means we're going to lock everybody into place. That rate of the forward reaction and the reverse reaction basically will equal each other. Any questions on that there? So initially here, if we look at this reaction, we have really no H2 or CO2 present. Again, that's just going to facilitate really this forward reaction happening. By the way, it is obviously not at equilibrium at this point, right? It's just sort of starting at this point. Can't be at equilibrium because we don't have any products made. At some point, again, we're going to build up enough of these guys on our product side where they will decide we would like to go back this way. And again, the key here till we reach equilibrium is the rate of the forward and reverse reaction at some point will equal each other. Another diagram of that, again, that plateauing part there where we get equilibrium basically achieved. And as you can see, past that point, it's able to really maintain that equilibrium through it. And like I said, really, if you don't do anything to it, it'll be able to maintain it for a pretty good time. If you do something to it, you can sort of mess it up as well. So for example, if we look at this reaction here where we have some H2O and some carbon monoxide making some hydrogen gas and a little bit of carbon dioxide. So take a second here and think about it. If we decided in this particular case that we wanted to add more water to this flask, how will the concentrations of everybody change, or will they not change? So take a moment, think about if you just had this guy that was at equilibrium, or this sort of guy at equilibrium. If you added some more water to it, what would you expect to happen to each of these concentrations? So take a moment and think about it. Okay, let's take a look and see what you think will happen here. So let's first off talk about when I add more H2O, what is that going to do in terms of sort of the reaction here? Would we expect, we'll start with H2, how's that? Do we expect more H2, less H2? H2 will be the same if we added some water to this. H2 should go up. I'm not sure if that was a question or not, but yes, H2 should go up. And the reason it should go up is because when we add H2O, basically we just added more reactants, right? Which means that water and that CO is not going to have a very hard time finding each other. And what that's really going to do is basically initiate the forward reaction to start to occur. And because the forward reaction starts to occur, as you correctly said, we would expect at that point to make more products, and we would expect the H2 concentration to increase. The CO2 concentration should also increase as well, again, because we're making products. How about the CO concentration? Does it go up? Does it go down? Does it stay the same? So if I am going to make products, right? What do I have to use to make products? Reactants, which means the amount of reactants should go down, right? We got to use some CO to make our products, right? Now, how about water? Water is kind of an interesting one. Water, we should initially see go up because you added it, right? So you artificially added it, so it should go up. But once it goes up, what then should it do? To start to go down as it starts reacting with the CO. What you might see with the water is it might actually end up a little bit higher than it started with because you artificially added it. But the trend you would see with that, guys, it should kind of go up because you added it, but then it should start reacting and sort of come back down as you do it. Any questions on that there? Yeah. CO definitely should go down, and it should probably end up less than what it started with because you didn't really add any more CO. So really the only one you kind of artificially on the reactive side sort of inflated was the water because you added it. So it went up, but then it should start to come back down as it starts reacting with the CO to make the products. So are you adding more H2O after initially putting? So basically this is a system that's already reached equilibrium. So we got this system that's at equilibrium, which means we pretty much got a little bit of everybody in there at this point. We're at whatever amount it is when it reached equilibrium. And then at that point to that, you decided to add some more water in this case. Yeah. Other questions? Okay. So let's take a look at this and think about what would happen in this same situation. We got this guy at equilibrium, but we added some H2 to this. How will everybody change here? In this case, as was mentioned, we're going to be actually adding our H2. Again, kind of very similar to what we saw in the previous one. When I add the H2, that's going to kick off which reaction, the forward or the reverse reaction? Yeah, it should really kick off the reverse reaction, really for the same reason. You just added more H2. It's going to be very available for the CO2 now to come together and basically go in the opposite direction. The result of that is the CO2 should go down. The CO should go up. The H2O should go up. And with the H2, we'll see a very similar thing that we just discussed with the water. It will artificially sort of go up because you added it. But then once it starts reacting with the CO2, we should start to see it decrease. Any questions on that there? Okay. All right, so I think we looked at that one there. So let's talk about the equilibrium constant and sort of the conditions. All right, so if we have a reaction such as this one, which is N2O4, it goes to a couple of NO2s, we could actually write a relationship that describes what is happening here. And it is what is referred to as K, which is capital K, not lowercase k like we were doing there in our kinetics. This is what is known as the equilibrium constant. It is also the letter that brings you this class. Everything's about K in here. This K is brought to you by the letter K as well. So the equilibrium constant in this case is really how we get it is the ratio of products to reactants. So we take basically the concentration of our products, again, divided by the concentration of our reactants. A reminder again, the little bracket is concentration, which means basically molarity in most cases. And we also do take the coefficients in the balanced equation. So we take the 2 here and it becomes the exponent. The coefficient here is 1, so that's why there's nothing written there. So in general, to write the equilibrium constant, we take the concentration of our products to the coefficients as the exponents, divided by the concentration of our reactants to the coefficients as the exponents. This gives us a value that is known as the equilibrium constant, which means for a reaction, this number should be the same or different every time you do it. Should be the same, right? It's an equilibrium constant. It is a constant value. As we will talk about, pretty much the only thing that will actually affect the value of the equilibrium constant is temperature. So if you change the temperature, the K value will change. And what I mean by that is if you have a K value for a reaction at 25 degrees, it would be one number. If you have a K value, say for the same reaction at 50 degrees, it will be a different number. But important is, if as long as you keep the temperature at 25 degrees or 50 degrees, you can basically do this reaction with whatever amounts of reactants or products you want. You could do different experiments. You could start with all reactants and get the same equilibrium constant. You can start with some reactants, some products, you'll get the same equilibrium constant. So that is the second thing I was talking about a little bit earlier that sometimes confuses people. They sometimes think, for example, like we did in the experiment earlier, that, we use different amounts of each of the reactants. We should get different equilibrium constants because we're not using the same amount. And equilibrium constant does not work that way. As long as you don't change the temperature, you keep it constant. You can start with whatever amount you want. It will always come to rest at the same ratio of products to reactants, and you'll get the same number when you calculate the equilibrium constant. Any questions on that? So kind of different points along the way in an equilibrium reaction. You can start anywhere along the way to figure out the equilibrium constant, again, as long as the temperature remains constant. This is the concentration of everybody. So this is also sometimes referred to as a Kc value. I'm going with C for concentration. Not 100% sure, but that does make kind of sense to me there. So Kc is for concentration. This is our first of 20 different K values we'll talk about this semester. Okay, maybe it's like 15, but it's pretty close. All right, but this is Kc. Yeah. And there's all kinds of different Ks in reality we will talk about, and the little letter on the bottom changes, and it kind of tells you what you're dealing with. For very shortly here, we'll talk about a Kp value, which deals with pressures and stuff like that. Yeah. Okay, so what does the equilibrium constant really tell us? Well, first off, one good thing about the equilibrium constant is there's no units typically associated with it. So it is just a number. So if I had a large value of K, what would that necessarily tell me when I reach equilibrium? Would I mainly expect to have reactants or products present if I had a large value? It would be products, just math-wise, since the equilibrium constant is products divided by reactants, right? In order to get a large value, I would need more products on top, right? Less reactants on the bottom, mathematically speaking. So you would expect to have more products at equilibrium. And vice versa, obviously, if we had a small value of K, that would be the opposite effect. You would have to have more reactants on the bottom. Small number divided by big number gives you a small number. And that means when we reach equilibrium, we would mainly have reactants that are present. So you may ask yourself, what is the large number and the small number? The really large number is anything above 1. Yeah, it doesn't seem like a big number, but technically anything above 1 would indicate a large value for the equilibrium constant. It would also indicate that you would probably mainly have products at equilibrium. Anything where you calculate the equilibrium constant, you got like a negative exponent going on there. That basically would mean that you have mainly reactants happening because you have a small value of K. So it's really important in certain calculations that we will do going forward to understand that concept as well. When you look at a K value, you know, it's just a number, but it does give you important information about what is happening with this reaction when it reaches equilibrium. And it also can help you with some of the calculations that we'll do later, depending on whether it is a large value or a small value. It gives you some options as to how to do some of the math. Any questions on that there? All right, so obviously here, if we look at Mickey, colliding over here with these guys, and Mickey goes upside down. We got a K value of 25. That means when we reach equilibrium, would we mainly have reactants or products in this case? We should have products again. 25 again is considered over 1, obviously a large value. And by the way, in terms of sort of range of large values, there are some that are extremely large, like, you know, times 10 to the 30. And there are some that are extremely small, like times 10 to the minus 36 type of number. So there are sort of ranges of equilibrium constant values that we'll come across in this class. And like I said, sort of understanding the idea of what that number means can help you with a lot of information about the problem. Yeah. No, you typically will not get a negative K value, but you can have obviously the exponent part negative and have a really small number like a scientific notation. But you know, K values are typically all positive numbers. Yeah. Other questions? All right, so let's talk a little bit about equilibrium. Homogeneous equilibrium is like a homogeneous mixture. And that means that everything is the same throughout is what a homogeneous mixture means. Homogeneous equilibrium means that pretty much everybody in the reaction is in the same phase. So in this particular case, everybody is in gases. And we can write an equilibrium constant like we just did earlier, taking our products over our reactants using concentration. But obviously, when we are dealing with gases, we oftentimes think about pressures. Right, our good PV equals nRT. That's the ideal gas law, yes. Pressure needs to be in ATM, yeah. Volume is liters, N is moles, T is Kelvin, right? And R is the gas constant, 0.08206, right? Or 21 if you rounded when you were learning it. So because we oftentimes will deal with obviously pressures involving gases, we can also write an equilibrium constant that really deals with pressures. And that is what is known as obviously the Kp, as I alluded to a second ago, P meaning pressure, right? So that is the partial pressure, and we still take the exponent. So as the coefficient, or the coefficient as the exponent. So the partial pressure squared because of the coefficient of NO2 divided by the partial pressure of N2O4, still products over reactants, but we use partial pressures. By the way, not so much in maybe some of these calculations, but later on, in most cases, when you're dealing with pressures, the standard unit of pressure is an atmosphere, yeah? So a lot of times in equilibrium problems, you want to make sure that your gases pressures are in atmospheres. Even if they, for example, tell you it is millimeters of mercury, and maybe they want an answer in millimeters of mercury or something like that, you do have to kind of usually convert it into atmospheres and then convert after you do sort of the equilibrium part of the calculation. So keep that in mind. Later on, we're going to do some equilibrium calculations, and sometimes it does involve pressures, and sometimes, like I said, they'll give you like the pressures in a different unit and ask you to give the answers in the same unit. But to do the equilibrium calculations, usually atmospheres is the unit you're looking for. And as you remember, right, 760 millimeters of mercury equals 760 torr, right, equals 1 atmosphere. There's other units of pressure, obviously, things like bar and stuff like that, but those are the common ones. Now, there's a Kc value, which deals with concentrations. There's a Kp value that deals with pressures. Are those values usually the same? The answer is no, they're not usually the same numerical value. They can be in certain weird case situations, but they're usually not the same numerical value. But they do tell you still the same sort of outcome. So if you have a large Kp value, just like you had a large Kc value, That would mean you mainly have products at equilibrium. In this case, you would mainly have probably products that are gases, providing a larger amount of pressure on the product side. And vice versa, if you had a small value of Kp or Kc, you would have mainly reactants. One important thing to remember is that no matter what the little letter is on the bottom of the K, they're all the same thing. They're all equilibrium constants. They're all really calculated the same, no matter what the little letter is. So they tell you sort of the same thing. Did you have a question? Yeah, you cannot have a negative any K value. So any K value, they all should be positive. Yeah. No, they really should correlate the same for the same reason, because in order really to get a large Kp value, right, you would need a lot of pressure, right? Which means they would have to have a lot of gas molecules probably on the product side providing that pressure. And if you had a lot of guys on the product side providing that pressure, that means you probably have more concentration over there on the product side and stuff. So they definitely should correlate perfectly with each other. They both should agree in terms of reactants or products. But again, just numerically speaking, they typically are not going to be the same value. Other questions? Now, there are some times when maybe you do want the Kp value and all you're given is concentrations, or maybe you want the Kc value and all you're given is pressures. So there is a nice little formula here in the box, which you do need to know, which will allow you to convert from one sort of K value to the other. So the Kp value would equal the Kc value. That is R, which is this R right here. The T there is temperature, also needs to be in Kelvin. And the delta N is the change in the number of moles of gases. So the delta N is the delta N of the products minus the delta N of the reactants. Basically, everybody with a G next to them in the equation, right? And we add up the number of gas molecules by looking really at the coefficients, right? So in the above equation there, on the right-hand side, there are 2 gas molecules. On the left-hand side, there is 1, yeah? So it'd be 2 minus 1 in this case would give you a delta N of 1. Now, what happens if I had, say, something like this? What would delta N be for that reaction here? Delta N, it would be 1 minus 2, which is -1. Now, it's really important to always do products minus reactants, because the negative here is important mathematically speaking, right? If you have that to the delta N, that's 1, which is just the difference, is a very different answer than if you took to the -1, right? -1 means mathematically you're going to take 1 over that value, right, when you do it. So sometimes people also make a little mistake there. They just go, the difference is 1 or difference is 2, but you want to make sure you do products minus reactants just in case you get a negative, because it would affect the actual calculation that you do. Also, by the way, you multiply the R times the T first and then take it to the exponent. Yeah, don't individually do it, right? So multiply that guy in the parentheses and then take it there. Question? Yeah.
And this only works for gases?
Yeah, so in order to have a Kp value or sort of write a Kp value, you got to have gases involved. So either they're all gases, or maybe you got a combination of some solid or liquid with some gas. But if there are no gases anywhere, you can't have obviously a Kp value, because technically there would be no gases producing any pressure or anything like that. Yeah. Other questions? All right. So in this homogeneous equilibrium, this is acetic acid, really dissolving in water, dissociating in water. And if we write our equilibrium expression here for this, we would do our products over reactants. But one of the things that we see there is actually water, which is a pure liquid. And typically in a reaction that involves water, the concentration of water really doesn't change all that much over the whole period. It does remain relatively constant. So typically when we do write the equilibrium constant, we actually do not include something like water that's a pure liquid. And the correct equilibrium constant for this reaction would be this one right here, products over reactants, where the water is not included. So I'll kind of jump ahead a slide or two, but basically when we look at an equilibrium, we want to write the equilibrium constant. We do not include anything that is a pure liquid because its concentration basically remains constant. And later we'll talk about it, but I'll just put it here as well. Anything that basically is a solid as well really will have no effect on the equilibrium. And you can just think of a solid like a rock, just kind of sitting there, right? And not really doing much. So those two things really are never included in the equilibrium expression. That means that really when you write your equilibrium expression, there's really two things that you do include, and that is anything that is aqueous because they're floating around ready to react, and anything that is a gas for the same reason. They're flying around and they're good to go in terms of reacting. So only really aqueous things and gases are included in the equilibrium expression. Anything that is a liquid and solid like we see in this one, we do leave it out of it. And as I said earlier, again, unless you're a rare person, most people don't use any units associated with it. Any questions on that there? All right, so take a second here, write the Kc and Kp expression if possible for these. See what you take a look here. So remember, no matter really what the letter is, it's all the same. It is products over reactants. We again want to make sure we use our coefficients as the exponents. So for our first one here, let's go up on top. Our Kc would be the concentration of NO2. Again, we do need to take it to the fourth because of the coefficient that is there, times the concentration of O2, which the coefficient obviously is 1, so we don't have to really put anything up there. We're going to then divide it by the concentration of N2O5, which also would again be squared because of the coefficient. Any questions on that one there? Can I write a Kp for this one? I can. I got gases all over the place. So really the Kp is going to be kind of the same deal, except it is the partial pressure, which is what the P stands for there. Also to the fourth of NO2, the partial pressure of O2 up on top divided by the partial pressure squaring it because of the coefficient of N2O5. Looking at the bottom one there, our Kc would be the concentration of H3O plus times F minus divided by the concentration of HF. And what about the water? Do I put it in? I do not put it into the expression. Again, it's a pure liquid, so you do not include it in the equilibrium expression. Question on that one there. Can I write a Kp for the bottom one? I cannot. Again, there's no gases involved, so you cannot write obviously a Kp expression. Any questions on how to write those? All right, so why don't we try one here? Some calculations. The equilibrium concentration. So these are some equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine. We got 0.012, 0.054, and 0.14. We want to calculate the Kc and the Kp values. So both of these here, take a few minutes and do. First off, in this particular problem here, we're given equilibrium concentrations. So right off the bat, we're looking for a Kc or Kp. Which one can we calculate directly? Yeah, we can directly calculate Kc because we are given the equilibrium concentrations. By the way, I'm pretty sure you understand this, but if it's the equilibrium constant that you're calculating, they need to be equilibrium concentrations, right, to be able to put in there, or equilibrium pressures, right? They got to be those, not initials or anything like that. So in this case, we could just do our Kc expression, which would be our products divided by our reactants. And put in our numbers correctly here. Looks like 0.14 up on top. We got a 0.012 and a 0.054. Gonna yield you like a 216. If you want to do a little sig figs like his chemistry, is like a 220 on that case. Yeah. Any questions on that calculation? Yeah. In this particular case, we're just dividing and multiplying basically. So all the numbers look like they got 2 sig figs. So that'd be 2. If your question is, should you round it going into the KP? I don't know. Technically, yeah, but I personally would probably rolled with the 216 myself on the calculator, to be honest with you. You'll get a fairly close answer, I think, on either one on the next part. But technically speaking, the correct KC value should be 220. And technically speaking, that's probably the value you should carry through to do the next part of the calculation. So doing that, now that we have the KC, we could use that formula that we saw earlier, which was the KP is equal to the KC times RT delta N. Here we want to figure out our delta N. Again, on the product side, we have a gas molecule and only one of them. On the reactant side, we got 2 gas molecules there, going to give us a -1 there for our delta N. We also need to take our temperature and convert it into Kelvin as well. So that's going to give us a 273 plus 74, looks like. So 273 plus 74 going to get us a 347 Kelvin. And I think that's everything that we need. So our KP here, I'll use the 220 and 0.08206. You could use 0.021 if you like. We're going to times it by 347. And again, we're going to take that whole thing to the -1. So if we do that there, taking it to the -1 and times it by a 220 there, gets us a KP value of about 7.7. Again, I think if you roll with the 216, you got a 7.6, which is, you'd probably be okay, but you technically should be using the 220. Any questions on either of those calculations? So this also demonstrates what we were talking about earlier, and I think was a question as well. Here we again see that the values of each of those are numerically different, but they both still tell us really the same thing. At a 220 and a 7.7, would I mainly have reactants or products at equilibrium? I'd mainly have products at equilibrium, right? And the idea here is if we mainly have products, probably have more pressure being associated with the COCl2 at equilibrium, and thus would account for our K values being high. Any questions on any of those there? Okay. All right, so let's try another one here. The equilibrium constant Kp is 158. What is the equilibrium pressure of O2? If I can go with this first one being the NO2. That would probably make it easier. Let's go with that one. I'm not sure if that's right or not. We'll go with it. So we'll go, the partial pressure of NO2 is 0.4. The partial pressure of NO is 0.27. And here we are looking for the pressure of O2 at equilibrium with a Kp value of 158. So take a few minutes here, see what you come up with. Look, so in this case, we have the Kp value given to us. We're also given some partial pressures here at equilibrium, or equilibrium pressures, and we're looking for what O2's pressure is. So it would make sense to write our Kp expression for this. So our Kp would be partial pressure squared of NO times the partial pressure of O2 divided by the partial pressure of NO2, and that also would need to be squared. That would equal the 158 value. At this point, we have everybody but the O2, so I went with 0.27 squared times the partial pressure of O2 divided by our 0.4 that's squared equals our 158. We're going to basically multiply this guy to the other side and then come back and divide that guy, right? That's over there. So if we do all that good stuff, we're going to take basically 0.4 and square it. We're then going to times it by 158. We're then going to divide that by 0.27 that is squared. And it looks like here we'll go over here, our partial pressure of O2 would be 347. And this would need some units as it is a pressure. So it should be the same units as all the other pressures that are there. Any questions on that there? Now, does this make sense? Well, it sort of makes sense, right? Our K value is 158, which means when we reach equilibrium, we mainly have reactants or products. We mainly would have products, as is a large value of K. That means we mainly should have NO and O2 there, which should be probably providing a majority of the pressure. And with O2 at 347, I think it's provided most of the pressure that's happening in that particular situation. Any questions on any of that there? Yeah. So if the question was like, what was it in torr or something? Yeah, you would definitely want to do the calculation probably like this in atmospheres and then convert it at that point. Yeah. It's more so a little bit later on, we'll talk about it as well when we kind of do some other calculations of all of it. But there's a specific spot as well. You want to make sure it's in atmospheres for sure in most cases. Those are sort of the standard units for like equilibrium is like molarity when you talk about concentrations, and then like atmospheres when you're talking about pressures. Other questions? So let's talk a little about heterogeneous equilibrium. Heterogeneous equilibrium is where we have obviously everybody in different phases. So here we got kind of a mixture of some solids and a gas. And as I mentioned a little bit earlier, just like the liquids, the solids basically will, not really participate. Again, you can think of them like a rock. You throw into water, they're just going to sink to the bottom. They're really not going to participate. In order for a solid to participate in an equilibrium, it would need to dissolve, right, in the solution. And once it dissolves in the solution, it then becomes aqueous ions probably. And then at that point, with their aqueous ions, they can participate. But the solid itself just sitting there undissolved basically will not have any participation. So in this particular case, we could write our Kc, which would actually just be our products, which would be just the CO2. And so an earlier question as well, here we have a combination of solids and a gas is involved. So we can write a Kp value for this one, which would be the partial pressure of CO2 in this particular case. So as I mentioned earlier, solids, liquids pretty much never put into the equilibrium expression, leaving you really just our gases and our aqueous that are put in there. By the way, if you had something like, let's just say this, right? Solid or something like that, just weird thing like that. How would we write the equilibrium expression here? It would be K is equal to 1 over A. Yeah. So you basically just put 1 on that side. So if you had something where just the reactants would be in the equilibrium expression and none of the products would be included, be them liquids or solids or something like that, then you just do 1 over the reactants, basically is how you would write the equilibrium expression. Any questions on that there?
That's also for concentrations.
Oh, I'm sorry?
For the concentrations, solids don't have a set concentration.
Right, yeah. So any K, which again, like I said before, the little letter on the bottom, no matter what the letter is, they're all really the same thing. They're all just equilibrium constants. So anything involving equilibrium constant, if you have a solid or a liquid, reactant side, product side, doesn't matter. You leave them out basically. Yeah. Other questions? So that's sort of what we're seeing here. Kind of these guys have really no effect on sort of what's going on above. In order for them to really have an effect, they got to kind of join in and become either gases or solid or aqueous. And at that point, they're obviously no longer solids, so we don't usually include them. All right, let's try one more here. Consider the following. At equilibrium, the partial pressures of each gas is 0.265. What is the Kp and the Kc in this case? Okay, let's take a look. So again, in this case, we're looking for both Kp and Kc. We are given pressures, which means Kp would probably be the best one to start with. We could directly calculate that. Our Kp expression in this case would be the partial pressure of NH3 times the partial pressure of H2S. And do I include this guy? I do not. Again, it's a solid, so that would be it, which means basically that's going to be 0.265 squared, basically. And that would yield us call it 7.02 times 10 to the minus 2, which would be our Kp value here. Any questions on that one there? Again, using the formula there that we saw earlier, Kp is equal to Kc, our RT delta N. In this particular case, our delta N would be our products, which one gas molecule, two gas molecules, minus none, basically, right? Which means our delta N is going to be 2 in this case. And let's see, our temperature is already in Kelvin, so that's good. So basically we got 7.02 times 10 to the minus 2 is equal to Kc, which is what we're looking for, our 0.08206, and we're going to times it by 295. Again, going to square it. So we want to multiply again in the parentheses first and then square it. So we're going to take 0.08206 times 295 and do a little squaring action. That's going to give us approximately, I think, 586 over here in that ballpark. We're then going to basically take it and divide it right to the other side. So we're going to divide it to the other side there. It gives us 7.02 exponent minus 2 divided by that number. Going to hit us a Kc in this case of about 1.20 times 10 to the minus 4 in this particular case. Any questions on any of those calculations there? Again, here we do see a couple of things. We do see that the Kp and Kc agree with each other. They are both large or small values. Small, which means when we reach equilibrium, we mainly have products in this case. Yeah, so anything that's a solid or liquid, not including the equilibrium constant, which means it really has kind of no effect on the equilibrium, what's going on, because it's, for example, the solid's just kind of sitting there basically. So you don't include it and you wouldn't obviously include it. So the delta N is only for things that are gases. So products minus reactants in terms of gases. Other questions? Questions on Kp, Kc, as I mentioned earlier, obviously, if you're going to directly calculate either one of them, they do need to be equilibrium concentrations or equilibrium pressures to go into there. There are products, there's no reactants. Is that what you're asking? Yeah. Oh, no, there would be, we would mainly have reactants at equilibrium. Yeah, yeah. Because it's a small value K. Other questions? Okay. So obviously you need to be able to do both of those things and convert between one and the other using that formula, which you do need to know the formula, obviously. Yeah. All right, so now that we talked a little bit about some of these equilibrium expressions, there are certain cases where, and as we sort of talked about with kinetics and, Hess's law and all that kind of stuff, that not all reactions necessarily do occur sort of in a one-step process. Sometimes it is a combination of several other reactions together. And we do see that with the equilibrium sort of constant as well. Sometimes you do need to manipulate an actual equation and the equilibrium constant that goes with it. When you do see an equilibrium constant sort of displayed, it is specific for exactly how the reaction is written, what's on the reactant side, what's on the product side, and stuff like that. But sometimes we do need to do some manipulation to those values. So for example, here, if we took A plus B goes to C plus D, we could have an equilibrium expression for it, which is right here. We also have another reaction where C and D then may be combined to make E plus F, which gives us this equilibrium expression. We could add them together, kind of like what we did with our mechanisms and what you typically do with Hess's law type problems. And again, anything that's on opposite sides of the arrow that are the same can either cancel or be reduced down. This gives us the overall reaction of A plus B goes to E plus F, which if we were to write the actual equilibrium expression for it, it is E times F divided by A times B. Now, how we get to this value is actually, if we look at the two equilibrium constants on the top, it is actually being multiplied together. If you multiply those two, the C and the D cancel, and you're left with the EF on top and the AB on the bottom. So sometimes you may be given a overall reaction and you are asked what is the equilibrium constant for it, and you may be given some individual equilibrium reactions. That's basically you add them together to get to that equation. If you need to add two equilibrium reactions together and you want the K value for the overall reaction, you actually multiply them, not adding. So you want to actually multiply here to get to the correct K value. So that's a very common way. Another very common way, kind of similar to like a Hess's law situation, is, maybe you don't need the reaction the way it's written. Maybe you need like the reactants being the products and the products being the reactants, and you need a reversal reaction. So if we look at N2O4 going to 2NO2, the equilibrium constant value there for that particular reaction is 4.63 times 10 to the minus 3. If we needed to reverse this reaction, basically make our products our reactants and our reactants our products, we write our equilibrium expression. And what it ends up doing to the equilibrium expression is you take 1 over the K value. It's basically the inverse of the original equation. So if we take 1 over the 4.63 times 10 to the minus 3, we get like a 216. When we say, hey, the equilibrium constant is 216, it is for exactly the way this reaction is written, where the NO2 is the reactants and the N2O4 are the products. If we said, hey, the equilibrium constant is 4.63 times 10 to the minus 3, it is exactly for the way the guy on the left is written, where N2O4 is the reactant, the NO2 is the products. So similar to sort of Hess's law, except in Hess's law, we change the sign, right, of like delta H. We don't change the sign here. We actually take 1 over the equilibrium constant to get the reverse reactions value. Any questions on that there? Couple other sort of manipulations that sometimes occur is, let's just say we had A plus B goes to C plus D, and we write the equilibrium expression of obviously C times D divided by A times B. Now, let's just say in this case, we didn't need 1 of everybody, but we needed 2 of somebody. We typically would take the equation and multiply everybody by 2, right? And if we multiplied everybody by 2, that would give us 2A plus 2B goes to 2C plus 2D. When we write the equilibrium expression, it is now the concentration of C squared times the concentration of D squared divided by the concentration of A squared and B squared. Now, unlike Hess's law, when we multiply the equation, we multiply the delta H by that number. What actually happened in the K value as we went from here to here? It didn't get multiplied by 2, but it actually got squared in this case, right? They got squared. So if we multiplied by 2 and ended up with basically taking the K value and squaring it, if I multiplied by 3, you would take the K value and cube it. Yeah. So if you have to multiply a reaction by a common number, how it affects the K values, you take the K value to whatever that common number is. You multiply it by 4, you take it to the 4th power, you multiply by 2, you square it and stuff like that. So that's another very common sort of manipulation that occurs with these type of reactions, where you might have to multiply by a common number. The other common one as well is if we went the opposite way, if we started with the 2A all the way across and we ended up with the guy on the bottom, what did we end up doing here? We ended up dividing by 2. And as we go this way, looking at the equilibrium constant, what happens as we go from the guy on the bottom to the guy on the top? The equilibrium constant becomes basically the square root, right? Is basically what that is. So if you divide by a common number, you take the K to that common number. So if you divide, if you multiply by a common number, you take the K to that number. So that is those 2 common manipulations that you do. So obviously, if we had to divide by a common number of 3, we would take the cube root and so forth, and depending on what number that you do there. Any questions on any of that there? So this would be a situation, again, like I said, where you're given a couple of different reactions, maybe 2 or 3 different reactions. You're going to use those to build an overall reaction that you're looking for. And you just got to sort of keep track of what you're doing to your K values as you do those manipulations. Any questions on that there? All right, we'll do an example of this next time, I think, and we'll lay it up here.